Tuesday, was looking at our orbital capacities, and in particular our capacities within an individual energy level. So for a single orbital, how many electrons can we get? 2. How many electrons can we get in an orbital type? Depends. Good answer. Okay. We have different orbital types. Those different orbital types have different orientations, which means we have different orbitals. Okay. So for an s orbital, we can only get 2 electrons because there's only one orientation. For a p orbital, I could get 6 because there's 3 orientations. Okay. However you want to remember that there's 3 orientations is up to you. Or even, I mean, really the level of the questions, that p gets 6. Okay. If you don't even want to remember there's 3 orientations, that's fine, just as long as you remember that p gets 6. For d, 10 electrons with how many orientations? 5. Okay. So we looked at the 1s. I think we did the 2s, or the 2. What if we did the 3? Did we do the 3? Question, so let's just make it the 3. Let's look at the third. In the third energy level, okay, what types are we going to have? S. We will always repeat the previous energy level. Okay? So that means for the third energy level, I have to have an S. I want to be more specific. It's not an S, it's 3s, because it's in the third energy level. What else do I have? I also have a P, better said 3p. Because I'm now at a third energy level, and I look back at my second had 2 types. Every time I move up in energy, what do I get? A new type. So 3s, 3p, I need a new type. Right? We end up with 3d. Okay? Why do we call it d? Because p was already taken. Okay? There are arbitrary terms, you just need to know what those terms are. Okay? Within the 3s, how many electrons can we get? 2, because there's only one orientation for the s, which means 1 orbital for that level. For the p, how many electrons? So, sorry, 3p. We get 6. Why do we get 6 electrons? There's 3 orientations. Each orientation gives it 2 electrons. 2 times 3, 6. D, 10. How many electrons in the energy level? The energy level is referencing, if we go all the way back to the table, the 3 in front. So of all of these things written here, where is the 3 written in front? 3s, 3p, 3d. How many electrons went into the 3s? 2. Is that in the third energy level? It is in the third energy level, yes. 3p?
Yes.
Yes. So I now have 2 plus 6? 3d?
10, yes.
Plus another 10, and I get 18. Cool. Make sense? Okay. Let's throw in one curveball. And because I don't really actually want to draw it all again, I'm just going to say we now move to the 4th energy level. How many electrons would fit in the 4s? 2. 4p? 4d? 10. Is that all my possible orbitals? We need another one because we moved up again in energy. Okay? So we have to have something else. 4 letter. Ooh, fancy. That began with F too. Okay. Our 4F is called F because it's fancy. Okay? How many electrons fit in the F? How do you know it's 14? We find the F block. How many columns in the F block? 14. How many electrons in the F orbitals? 14. How many electrons in the 4th energy level? More than I can count, but we'd add up all those numbers and that would be our total. 32. Okay, you guys did that better than I did. Okay? Kind of makes sense? Yes. Sky. Just kidding. Okay.
I have a question.
Yes?
I'm trying to relate that to like this thing, but it has nothing to do with this, right? That's
Not
what's
directly.
throwing me off.
So what is being asked is if we looked at, which there's a reason why I've never shown this, we saw something like this. Do you have 8 dots in that one? Something like that. So have you seen these kind of diagrams? There's a reason why I haven't drawn any of them. They're stupid. They may help you, that's fine. That doesn't make you stupid. It's still just a dumb diagram. Okay? What's the issue with that diagram? Very two-dimensional. What happens, what's our first energy level look like? A sphere. So, okay, sure, that looks fine. And it fits 2 electrons, cool. What's our second energy look like? A sphere and dumbbell. That looks like an awful lot like just a sphere. Okay? Why are they showing it just like a sphere? It's coming from a level of complexity. This kind of discussion is something that is said that you aren't ready for understanding orbitals, so we're going to draw them this way. Okay? Unfortunately, whether you like it or not, by being in this class, you're ready for more than that. Okay? There is useful information in it. I don't like it because it oversimplifies things way too much. Okay? Yeah, but that's about really all I can say to that. So don't worry about, I don't understand why that doesn't match. It's because it shouldn't match. Because it doesn't match. Okay? What if we moved up to the 5th energy level? What are my orbital types? S, P, D, F. What was that? Then another letter. What is that other letter? Actually, I think it is G, believe it or not. Okay. How many electrons can we fit in the G? Ooh, I don't know. Let's cheat and look at the periodic table. Oh, there isn't a G block. Why is there not a G block? We haven't found it yet. Okay. We haven't built an atom large enough to fit that many electrons around it. We aren't at the G block yet. Okay. We would need presumably at least 3 more elements to hit the G block. Okay. Because the very next to fill will end up being an S. Okay. And then hopefully we would bring in that G as another layer in. Okay. We aren't there yet because we can't get big enough. Okay. Will we ever get big enough? Possibly, but probably not. Okay?
So when you're talking sublevels, theoretically we could go to whatever number, but is 5 going to be like the greatest number you can go to?
Is 5 the greatest energy level?
No.
What's the highest energy level? 7. How do we know we have 7? There are 7 rows in our periodic table. So we've gotten to the 7th energy level. That does not mean we've made it to the 7th sublevel, okay, or orbital type.
Sublevel?
Yes. We've only made it to the 4th, the 4F sublevel. Okay. We have made it to the 5S and the 5P and the 5D, which might be an interesting question. How could we get to the 5th energy level if we haven't cleared the 4th? Stuff got weird.
Yeah.
Okay. And that's where people say, oh, well, there's an exception. It's not so much as an exception as that we haven't explained why that would happen. Okay. So if we were to look at another representation, I've heard a couple people already complain about this, but we're looking at this one anyway. Deal with it. Okay, we start at our first energy level. We only have 1 orientation, so there's only 1 line. We move up to the 2nd energy level, and what happens? We get a new sublevel. So it splits into 2 parts. Okay? So I have the S, and then that new sublevel has 3 orientations. So I get 3 new orbitals coming out of it. So each of those lines is representing an orbital. We move up to the 3rd energy level. What happens? We get another sublevel, and we have the S, the P, and the D. What happens if we move up to the 4th energy level. Okay, we get more. All right, but before we get to the more, let's start to process our way through this. Okay, because we want to come up with the fill pattern. And we started to do this already. We looked at the electron configuration for hydrogen and helium and lithium. All right, so if we drew that out again, the electron configuration for hydrogen. Hydrogen only has one electron. So when we're talking about the electron configuration, I want to know where every single electron for an atom exists. Give me the location. So hydrogen only has one, so it's easy. I just have to explain where one electron is. Okay, where is that one electron?
One sphere.
It's in the first energy level, also known as a sphere for its orbital type, which sphere is too many letters. I know it's fun to say.
Yes.
S, but now I need to specify how many electrons were there. 1. 1s1. What if we made it now helium? Well, helium has 2 electrons. Where did its first electron go? 1s1. It went to the exact same place that hydrogen's first electron went. Where did its second electron go?
The same sphere.
1s1, because each orbital fits 2 electrons. It would get really repetitive, particularly if we had to do an octium, which is 118, if we had to write each of those codes for every single electron. So we do a shorthand. Okay? Like if we did 2 times 2 times 2 times 2, our shorthand becomes 2 to the 5th power. Okay? We're doing the same kind of shorthand with our electron configuration, and this becomes 1s2. Lithium.
1s2, 2s.
Lithium has 3 electrons. The first 2 are going to go into the 1s orbital. Where's the next electron go? 2s1. Okay? You might say, well, we could do that off of our diagrams. We just got to draw the diagram every single time. How many of you are going to be excited about doing that? That's what I thought. Okay? Our periodic table gives it to us. First row, we can only fit 2 electrons because 1 orbital. I can only get 2 electrons into the 1 orbital. Second row, how many columns? In the second row, there's 8. So our row goes all the way across the periodic table, full on grid. Yes, there's some empty stuff in the middle. Don't worry about it. Right? We got 8. Why are there 8? We can fit 8 electrons. Each orbital holds how many electrons? 2. So are there 8 orbitals? There's 4. Let's take a look at the lines that Mike drew earlier. Mike's not a horrible person. He drew 4 lines. Okay? That's where those electrons are going. If we want to get more specific on them, that's where we would specify our S and P. We go to the 2s. And you might say, well, why do I have to go to the 2s? Why couldn't I go to the 2p? The periodic table gives it to us. Second row, 2. Lithium and beryllium are in the block known as the S block because if we stop adding electrons with any element in there, we're stopping at an s orbital. Okay? So our electron configuration for lithium is 1s2, 2s1. Easy, hard? I heard an easy, so let's calcium. And by hearing the easy, I'm saying that you thought it was easy, so I'm making it harder. So how many electrons does calcium? I need 20 to get to neutral calcium. Where's the first electron go? 1s. There it is. Second electron. 1s. So I can condense that as 1s2. Third electron. 2s. Fourth electron. 2s. So that can become, where's the next electron go? I'm still in the second row. I got to see if there's another column in the second row. Is there another column in the second row? What does it start with? What's the letter that starts with that next column? B. So yes, there's another column in our second row. The columns are the vertical lines. Lithium, beryllium. If we continue across, where's that stupid ruler? You may have to jump for this.
Use relation with the columns if we're talking about a specific element. Where the column is.
How many electrons went into the first column?
Okay, one.
Okay, how many electrons were in our second column? How many electrons in the first column?
Or four.
1. There were 2 more underneath it. How many electrons in the second column? 2. How many electrons in the... Okay, 3 electrons in what energy level? What energy level? The second energy level. Okay. The second energy level subdivides into 2 orbital types. One known as the, it's a fun sound, S block, and the other category is known as the P block. If I move to boron now, we're adding 1 more electron after 2s, still the second energy level, tick, 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 but it's in a new block. It's in a new block. What should I do? Name it. What am I going to name it? P. But it's because that's the second row, I'll call it 2p. Or not, no, that's, I'll avoid that one. I can't help it. Or not 2p. 2p, and at that point we'd only specified 1. That gets us to boron. Where am I trying to get? So am I going to have to add more electrons? Yes. How many more electrons do I need to add to the 2p? 5 electrons to a 6 total. Okay, so that 2p becomes 2p6. I'm now at neon. Is that calcium?
No.
What do I have to do?
You get to your third.
I need to add another electron. There's not another column, so what do I do? Go down to the next energy level, which would be the 3 in which block? First column, 1. Next element, 2. Then I move across. What do I move across to? 3p. Do I have to fill that 3p? Yes. Move to the next one. And this is the fun one. Argon. After the 3p, where should I go? 1s, 2s, 2p, 3s, 3p, 3d, 4s. What came after 3p? 3d. What element comes after argon? Potassium. Where's the last electron for potassium? It is in the 4th energy level because we're in the 4th row. Which block is it in? The S block. And it would then be 1, but I wanted calcium, so I add 1 more and it becomes 4s2. Why is that now all of a sudden weird? I skipped 3D. Why did I skip 3D?
You didn't skip it. You're going to come to it next if you had to go.
I could come to it next, but when I filled, I went 1s to 2s to 2p. Why did I not go 2s to 3s? Why can I skip the 3D, but I couldn't skip any of the others? So there's a good answer. We might go, well, I don't know why we can do that. How am I ever going to remember that I'm allowed to skip it?
Because it's on the periodic table.
Periodic table gave you the order. You don't have to remember it. The periodic table just told you what the answer was. You just have to follow what the periodic table tells you. Okay. It's of course not good enough, and we're going to have to explain that. But the periodic table gives it to you. So calcium goes to the 4s2. We end up not filling the D. How do I get into the d orbital? What is the next element after calcium? scandium, Sc, 1s2, 2s2, 2p6, 3s2. You all better be writing this because I'm writing it too. 3p6, 4s2, and then 3d1. But the d orbital's in the fourth row. I know. That sucks. It's still the third energy level. The d orbitals are offset by 1. Okay? Guess what happens when you hit the f orbitals? They're offset by 2. Okay? Which I heard another answer up here, don't know, don't care, because I think I just heard don't know, but I added the don't care. We don't care about the f orbitals because we aren't going to have to worry about those. We don't have to fill those. Okay? If you move into 151, I've seen some instructors ask for electron configurations down there. Okay? So that's how we get into the 3D. So this is numerically perfectly makes sense. We go 1, 2, 3, 4, 3. That makes no sense. Okay? Again, the periodic table gives it to you, but the question becomes, why does it do this? Okay? Why does it offset? And it's not because it's a massive exception and science hates you. Okay? If we go through and look at our diagram, what happened as we moved up? What is changing? Energy. What happens in the next move up? The energy goes up. Does it go up by the same amount? No. It goes up by less, which means the orbitals progressively become closer and closer and closer in energy. Remember when we filled the 3p, or sorry, the 2p? We put the first electron in. I said, where does the next electron go? We had two options. It could either go on the same one or the next one. And went to the next one because we want to go to the same energy first before we pair them up, because that's higher in energy. Okay. What happens is we get further and further up the periodic, or up in energy. All the orbitals start to get closer and closer in energy, which then means the electrons get to decide where they go. Oh, crap. An inanimate object that I can't see or understand is now deciding something for me. That's not particularly fun. Okay? Except it is deciding the exact same way you decide. This tiny little object's doing the same thing I am? Yeah. Yeah, it is. Okay? So what we're talking about is we're all the way up in here. Okay? We got to the 3p, and instead of going from the 3p to the 3d, where did we go? We went to the 4s versus the 3d. Okay? So those are our options. Okay? Can everybody... So I'm going to make that yellow one, or 4, a black line. Hopefully it stands out a little bit more. You can at least tell the difference between the green ones. Yeah. We okay with that?
Yeah.
Whoops. Kind of needed that one. Okay. So here's what we're going to decide, or how we're going to work this, and why it would potentially go to the 4s instead of the 3d. It's a little concept known as symmetry. If I'm given the choice, I need to place one electron. Okay, so this is fully substituted. So is that one symmetric? Yeah, all the orbitals are completely filled, perfectly symmetric, beautiful. I have to add one more electron. Where do I want to add that one more electron? Into a place where there's only one option, or into a place where there's 5 options? Why would I go to one option versus the 5? What do you mean?
Because it's just one electron, so it only needs to go on one.
I only need one orbital. Okay, remember I said something about symmetry. If I place one electron into 5, can I split that evenly? No. Could I split that one? That's not too bad. Well, symmetry is not that big of a deal, right? Okay, so let's take a little adventure here. We can all close our eyes. Yeah, close your... You're not supposed to be looking at me for this one. Okay. So, and I see people intentionally opening their eyes. That's not fair. Okay. If you got your eyes closed, okay, we can drift out of chemistry, and we can drift to the most attractive person you've ever seen. This is why your eyes were closed. And visualize taking one hand, don't hit them, but cover half of their face. Okay? Mirror that, the visible half, onto your hand. When you remove your hand, is it exactly the same? Okay. If you cover half of someone's face, someone that we have identified as being attractive, okay, and you just mirror the other side across. You stuck a mirror up to someone's face and just looked at that result. Okay? And then you take a picture of that, and then you look at their face without your hand or mirror in the way, and you compare those two, they are nearly identical. Envision the most ugly person that you can think of, and again, eyes closed. And when you do that, do the same process. Is their face mirrored across the same? Typically not. And you can open your eyes now. What we envision as beauty is symmetry. Okay? Why is a good question. I don't know. Because that same symmetry that we are visualizing and placing on aspects of beauty, electrons are doing the exact same thing when they decide what orbitals to populate. So when we're looking at our fill pattern, we jump from the 3p to the 3d, or sorry, what is that one? 4s, because that is more symmetrical than partially filling one orbital of the 3d. That's neat. Symmetry plays a massive role in how we apply and understand electron orbitals and life in general. Okay?
So,
how much of that do you need to know? Yeah, it's kind of up there. I'd probably say that's an extra credit question. Okay? If you can apply that correctly. If you can't apply it correctly, then you don't get the extra credit, and you just move on. Okay? What you're responsible for is how do the electrons fill? Oh, I don't want to memorize how the electrons fill. Don't. It's on the periodic table. Okay? Make sense? Mm-hmm. Question?
So when you get to the when you fill up the fourth sublevel or the fourth energy level, and doesn't it skip off to 5 before it finishes off the fourth?
As we continue to move up and up in energy, what happens to our orbitals? They get closer and closer and closer in energy. Do we continue to see weird exceptions like this one? Yes. Does the periodic table also give us that information? Yes. We don't even have to know that. We just have to use the periodic table. Okay? The other option is using this weird filling diagram for electron configurations, which people seem to really like. I don't, because I can't draw straight lines or grids. Okay? But the idea is you have a nice grid like, and you go through the 1s, and then you loop back down and restart through the 2s, you loop back down, 2p, 3s, loop back down. It's like a stitchwork thing. That explains your fill patterns. And notice that as we get further and further up, we run into more and more exceptions to how things fill. Okay? So, what do we do with this? Well, this ultimately is going to come back to this concept of valence electrons. Okay? And I'm kind of irritated now because I actually erased it. But if we looked at the electron configuration for scandium, we had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Already writing that out, I lost attention span. I couldn't figure it out. That's a lot of stuff to write down. I wonder if there's a shorthand for that. Yeah, there's a shorthand. What can I go through and do? I can say all of that was already described by what element? It's not the previous element. 3p6 ends at argon. So I can take argon's electron configuration and I need to add to it what? 4s2, 3d1. There's my electron configuration for scandium. Sweet. Okay? I didn't have to write all those individual things out. Did you guys write them all out again?
So if we're going to rewrite it like that, we have to have the brackets around argon?
You need the brackets around the argon, yes. Okay? If we were going to look at, say, a different element, and you can tell where my biases lie. We looked at carbon, 1s2, 2s2, I keep doing that, 2p what? 2p2. Okay. But since you mentioned 6, where'd you get the 6 from?
I was looking at calcium.
I don't know how that works either. But there's 6 on the periodic table. Our atomic number for carbon is 6, so people like to say 6. Where do we find that 6 in this electron configuration? 2 plus 2 plus 2, 6. If you did it right, the superscripts will add up to the amount of electrons in your structure. If you did it wrong, those won't match. Okay? Nice simple trick if you had like a multiple choice question. Take a look at the practice exam. Okay? So if we had this, carbon. Okay? Carbon now is an atom. Okay? It's got those electrons around it. It's got a nucleus. That atom is now going to go out and react with another atom. What is it going to react with? What's the first thing that that carbon is going to show another atom? Too fancy of a word. The outermost electrons. Right? Why would it show the outermost electrons? Well, when you go up and introduce yourself to a new person, do you strip down and say, howdy? Or is it a little bit more of, hi, how you doing? Nicely clothed and everything nice and happy? Okay. Okay. We don't show the inside right away. Okay, just go on Facebook. We show what we want other people to see. That's our outermost shell. That's what's happening. So when I look at carbon, do I really want to talk about all of those electrons if I'm going to say move into a situation like Lewis bonding? Okay. Which of those electrons are most likely to interact with another atom? And the outermost ones. What are the outermost ones? The valence electrons is the name for them. And I think I heard the number 2. What 2? This 2? It's going to be the energy level. The highest energy level are my valence electrons. So when I look at carbon, carbon has how many valence? 4. By looking at the big letter number above the upper right-hand corner, we add those numbers. We get 4. So carbon has 4 valence electrons. So, well, I don't want to have to draw out the electron configurations every single time I look at this. I wish I had a tool that had this information already embedded on it. Oh, we do. Carbon, what is the column name for carbon? 14. 14 has 4 in it. What's the Roman numerals? 4. How many valence did carbon have? 4. Okay, let's see if that pattern happens to be consistent. Let's look at hydrogen. Hydrogen was what electron configuration? 1s1. How many valence electrons does hydrogen have? 1. What's the name of its column? 1. Beryllium? Beryllium was 1s2, 2s2. Valence electrons would be the highest energy. How many valence do we have? 2. What's its column name? 2. Guess what? Your valence electrons are already told to you at the top of each one of those columns. Okay? Kind of neat. Okay? We will need access to the valence electron information very quickly and readily. That needs to be a fast periodic table. That's the number. Okay? Kind of makes sense? And we continue. So back to chapter 5. Okay? Periodic table is awesome. Remember I was talking about the S block, the P block, the D block, F block? Some people had a hard time blocking those sections out. And I don't blame you, because we're looking at that and all we see are lines and letters and numbers and it gets confusing. So your textbook has a pretty nice image where it's colored them differently so that we can see them. Okay? That's your distinct kind of blocks. Notice we have some weird exceptions with helium. Where does helium appear to be located? On the right-hand side in the P block, and yet it's not part of the P block, it's an S block. Okay? Helium and hydrogen are kind of weird because they are so small that they don't fit the rest of the periodic table. And sometimes you will see periodic tables with helium shown not just above neon, but also shown above beryllium, because they have the same configurations. You will also find periodic tables that show hydrogen not just above lithium, but also above fluorine, right? Because they have similar electron configurations in certain states. Okay? They're all coming back to their electron configurations. So the periodic table, lots of information. We got symbols, we got atomic numbers, we've got the electron configurations, we've got valence electrons, we've got atomic mass. Okay? Is there more? Probably. Let's see what the rest of the semester holds. Oh, bummer. What do we see about that? 10. So a couple people actually called it out while I was walking around. Like, this is really what you're trying to say within this question? Like, it's kind of a jerk thing to do. Believe it or not, I have missed that kind of question on a test. Read your question very, very carefully. How many electrons fit in one p orbital? Doesn't matter the type, it's 2. How many electrons fit in the d orbitals? Okay. Okay. Be careful with how you read a question. Why does the atomic radius increase down a column? Electrons increase. Okay, I like that theory. Let's stick with that. Electrons increase. Why does the atomic radius decrease from left to right in the periodic table? D orbital, beryllium to boron. Is there any d orbital?
Yes.
No. That's the second energy level. There's no d orbitals, so d orbitals doesn't count.
Is it like protons and electrons are like magnets, so they want to come close together?
So within a column, there's no protons then.
It's because as you go from left to right, you increase protons and neutrons the same amount of space because you have the same energy level. So there's less.
Very, very close. What do you mean same energy level? Same energy level of what?
Same level of valence electrons.
It's your electrons. Size is dictated according to electrons. When we go down a column, where are the electrons going?
Oh.
To the next highest energy level. When we go across the column, do they go to a different energy level? No, they stay at the same level. If they stay at the same level, what should happen to the size? They should stay the same, but it decreases. Why does it decrease? Now you can bring in the evaluation of the protons. It's not just that we have more protons. Down a column, we have more protons. It's that the electrons are going into the exact same energy level. It's a balance of both. So even saying electrons increase for question 3 is still technically wrong, because electrons increase left to right as well. Okay? This is a very challenging concept. Okay? One that we cannot answer until we have electron configurations. Once we have the electron configurations, we can then predict what's happening. The outermost electron for lithium, so I don't want its valence, just its outermost electron. The outermost electron for lithium is what? It's S1. What energy level? 2. For sodium? 3s1. Are electrons going in a higher energy level? By definition, that is further away.
Yes.
Okay. When we move from lithium to beryllium, what happens? The electron's located in the 2s orbital. Okay. Well, if it's in the 2s orbital, is that further away from the nucleus or closer to the nucleus? It's the exact same space. What else changes now? The number of protons. The proton, that extra proton, is a magnet. So we now had 2 magnets that weren't attracted to each other, but I made one of them super, super strong. What now happens? Zip, zip, zip. And they're now attracted to each other. Same thing is happening with our atomic radius. Tricky concept. And it all goes back to understanding our electron configurations. Within a column, I fully expect you to be able to understand and grasp that concept. Within a row, that is more advanced. That's kind of like the A to high B grade. If you can explain that, then that's where you're aiming for. Do you not want an A? Then don't worry about that. Okay? Ionization energy is our next fun topic. Okay. What is our ionization energy? Actually, sorry. On the periodic table. I want this periodic table. Yep, periodic table here. So, within a column, because remember, one of the things you'll get tested on is multiple choice. And in multiple choice, what could I easily ask? Which atom is bigger? Rubidium or sodium? Rubidium, I think, is that not one you need to know? Okay, potassium or hydrogen? Potassium. Okay. To answer that question, I saw a lot of you shift your attention to the periodic table. Interestingly enough, everybody, even that side of the classroom, shifted their attention over here. Yeah. Maybe, but there's one right there. Just so you're saying. I know, I'm the focal point. Okay. So it might be nice that if you had a periodic table, that information was specified for you. The periodic table doesn't directly say that information. We'd have to interpret it. Unless, when we got our exam with the periodic table that we can draw on, we can write that information down. Which element was bigger within a column? Francium, bottom left, or hydrogen? Francium, what happens to size? Increases down. Bigger. What happens left to right? It gets smaller left to right. Now when I'm asked a question, I don't have to think about it. I go back to my page where I drew this out, and I say, well, that one's bigger, bigger. Where are they relative to each other? Which line, which row? Answered. Okay. There isn't this extra thought of, okay, what happened within the column, what happened within the row. It's already drawn. You've purged that information. You can't, or harder to forget it. Make sense? Put it on your test.
So if you were looking at iron and francium is going to be bigger than iron, correct?
Yes. Francium will be bigger than iron. Why? I want two reasons.
It's also, it's below.
Francium is at the very bottom of the periodic table, so it's already going to be a big element. Okay? I don't quite accept that. Just it being on the bottom doesn't mean it's the biggest.
It's also weight at the bottom.
Cesium then. Cesium versus iron. You can't tell me cesium. You can't tell me cesium is now the largest element. Because it's not. So that analysis doesn't work.
Lower and to the left than iron?
That's the key word. Than iron. You are comparing two things. What if I ask you to rank 4 elements? What are you being asked to do? Rank 2 things multiple times. Okay? Do not rank. If you got 4 things to rank, you're not ranking all 4. You're ranking 2. Then you rank another 2, and another 2, and another 2 until it's all done. Never just like a big old plate of dinner, right? You got your dinner, you say, there's food, mouth. Doesn't happen. You take little bits and pieces out of it. Okay? At least it doesn't happen efficiently, even if you tried to do that.
So will we ever be asked a question like fluorine versus argon? Since argon's further down, but it's also more...
So there's an interesting question. Can you be asked things that are not in the same column or row? Yes, but you can only be asked in a way that you can do from the trend.
Okay.
So if we compare fluorine to argon, what we want to do, because they're not in the same column or row, is find what they have in common. What does fluorine have in common with argon?
Yes.
On the periodic table.
They're red.
Keep going.
It's in the block.
No. No. It's a really weird one. They both have in common neon. What do I mean? I look at neon. Neon's in the same row as fluorine. Which one's bigger, fluorine or neon? Fluorine, according to my trend. Okay, so fluorine I know is bigger than neon. Now I can compare argon to neon because they're in the same column. I now have something in common between them. Which is bigger, argon or neon? Argon. So I know argon and fluorine are both bigger than neon. Was that thing in common helpful to distinguish the two? No. Okay, maybe if I look at chlorine. Chlorine is also in common. Which is bigger, fluorine or chlorine? Chlorine. Which is bigger, chlorine or argon? Chlorine. So I know fluorine and argon are both smaller than chlorine. Was that helpful to distinguish the two? No. Will I ever ask on that diagonal? No, because you can't do that from the trend. You would have to know the answer. Okay. The opposite diagonal, say fluorine and sulfur, yes. By doing that same idea, you would find what's in common between fluorine and sulfur, and that would be oxygen or chlorine. Okay? So, ionization energy. Okay. Ionization energy is the amount of energy required to remove an electron in the gaseous state. Okay, I always have to read that off because I almost always forget it. Okay. So we have an atom, any one of our elements, all by itself, okay, which then means it's in a gas because it's not near any other elements, so it by definition is a gas. Okay? And I go up to that element and I pinch an electron and I remove it. Okay? The amount of energy it takes for me to take that electron and remove it is the ionization energy. Okay? So let's ignore the trend for the moment. Okay? Which atom would it be easier to remove an electron from? Francium or hydrogen? Why would it be easier to remove an electron from francium? It's larger, which means where are the electrons? Further from the nucleus, which means they are higher energy. By being further from the nucleus, they are also closer to the vacuum. What are we doing with ionization energy? Removing the electron to the vacuum. If it's closer to the vacuum, that's really easy to do. Hydrogen, having its electron in the 1s orbital, is as far away from the vacuum as we can possibly get, which means to remove the electron from hydrogen is incredibly difficult. Okay? Is it possible? Yes, it's always possible.
Hydrogen bonds, probably something to do.
No, don't bring that in, at least not yet. Okay? So, in general, your ionization energy increases as we go from the bottom to the top. Why? What else changes as we go from bottom to top? Size. What happened to the size? It got smaller, which then means harder to remove the electron to the vacuum. It transitions opposite of size. In general, ionization energy increases as we go from left to right on the periodic table, because what happens as we go left to right on the periodic table? Atoms get smaller. It tracks with size, or kind of the opposite of size. Okay? And our explanations kind of go to nucleus being more positive, but they're really just the inverse of our atomic radius. Okay? There is one kind of nasty little thing here. Anybody notice any key words in those statements that might make you go, wait a second? What does in general mean? Generally, I'm the tallest person in the classroom. How tall are you, Johnny?
6'1".
Damn it. Generally, yeah, I think I trump everybody in all regards there. Generally, I have the longest hair in the classroom.
Generally, you probably have more degrees.
That's not right. There are people that have longer hair. And man, I'm also Trump there. Nobody has shorter hair than me. What the heck? Okay.
College degrees?
But generally, I have more college degrees. That's probably true too, though. Okay. Generally means there are exceptions. Okay. That gets nasty and everybody freaks out. Okay. There really isn't an exception. There's understanding the principle behind it. What is the principle due to? Electron configurations. Yay, those fun things that we looked at. So when we look across our trends, your ionization energy, so each of those points is representing an element and its corresponding ionization energy. So hydrogen starts us off. Okay. Generally, The ionization increases as we go left to right because the atom gets smaller. And what happened as we go from hydrogen to helium? It increased. Okay. Generally, as we go down the column, the ionization decreases. So as I go from hydrogen to lithium, it decreased. What happens as I go across the second row? Lithium to beryllium. What should happen to the ionization energy? It should increase. As I go from beryllium to boron, it should increase. And yet, what does it do? Decreases. Generally, there's an exception. What happens when I move from boron to carbon? It increases. That fit the trend. Carbon to nitrogen, it increased. Nitrogen to oxygen, it decreased. So we have exceptions. Oh, exceptions. Exceptions are a load of crap. There's no exceptions. You just didn't understand it right. Why do we see the change between, let's say, beryllium and boron? What was the electron configuration for beryllium? And in particular, all I care about is its valence. 2s2. How about for boron? I'm going to draw that a little bit lower, I think. And officially, actually, I don't even care about its valence. I just want that last electron. So 2p1, right? We're going to do the valence. I changed my mind. 2s2, 2p1. If I look at the ionization energy, what am I doing? I'm removing the last electron. So ionization energy in purple. Boof! Beryllium becomes... What is ionization energy? Remove an electron. So would it become 2p1? No, it becomes 2s1. What happens with boron? It becomes 2s2. Okay. You remember how we did the whole eye closed example, looking at beautiful people and all that fun stuff? Okay. Beryllium. Did it start symmetric? Yeah. Did it become more or less symmetric? Less. You are now the most beautiful person you can imagine, or handsome, however you want to look at it. And you are then told that we can make you less beautiful and handsome. How many of you are like, yep, sign me up? Anybody? Sorry. Nobody wants to do that. Okay? If you're beautiful, you're like, I'm going to stay beautiful. I'm not going to do that. So what does that mean happens to the energy? To make you do that, we'll probably have to tie you down. Put in a lot of energy. Okay? That energy now spikes. And beryllium's energy should go up significantly. But that made sense. Beryllium was supposed to go up. What happened to the boron? Did it start symmetric? No. So it is ugly. What happens when we remove that one electron? It becomes symmetric. And symmetry is beautiful. You are now the ugliest person. What happens if someone comes along? We will make you beautiful. Yeah, sure. Why not? Always want to be pretty. Okay. That is now a very low energy transition. So the energy required to do that drops. So beryllium spikes and boron drops. What do we see? An exception. What happens at each of those little weird spikes? The exact same thing. All going back to the symmetry of those orbitals. Yes?
When you wrote those up there, we're just assuming
Neutral.
1s is there, right?
Yes. All I was asking for was the valence. Okay. This is another one of those challenging, like mind messed with kind of questions, which kind of puts it at that extra credit level. What would you be expected to do? Know the general trend. You will be asked questions that come off the general trend. So I could ask you to rank boron, carbon, and nitrogen with their ionization energies. I would not, however, ask you to rank beryllium, boron, and carbon, because that involves the exception in understanding that extra little bit of information, because you won't have the ionization energies. All you will have is the periodic table that you went back to and then said, oh, I need to draw on not only the atomic radius, but also what? The ionization energy. The ionization energy decreases Oh, geez, that says decrease. And decrease. Okay? With that, I know you guys want to get out of here, but I promise I'm pretty sure, almost positive. Electron affinity, fancy thing, opposite of ionization energy, not in the textbook, don't stress. The average of those is electronegativity, the ability for an atom to grab or hold bonding electrons. Where is this important? Everywhere. Okay? Doing Lewis structure requires understanding of electronegativity and of valence electrons. The electronegativity, it comes off of a chart. The most electronegative is fluorine. The least electronegative is francium. There are weird exceptions in between. You don't need to stress about those. We need the general trends to be able to predict and manipulate. If you don't want to memorize electronegativity, there's a convenient one that you've already done called metallicity. Our most metallic element is metallic, francium, and our least metallic, most non-metal, fluorine. They run opposite directions of each other. Okay? Ionic charges I will talk about on Tuesday, which is a bit unfortunate, but I think you guys will have it pretty well. Okay? This is the thing I wanted to get to, our Chapter 4 and Chapter 5 summaries. These slides go through and summarize the big things to get out of Chapter 4. I've had some people ask, well, what do I need to know about the scientists? Dalton did what? You should know that. Thomson did what? You should know that too. Curie did what? That one's tricky because Curie was only mentioned in the lecture. You might want to go back and watch the video. Okay? Protons, neutrons. It's the general principles of the big topics that came out of Chapter 4. We have the same thing in Chapter 5. Okay? For those of you looking for those slides, you can take pictures, that's fine. They are also posted on Canvas. Okay? You already have access to those. So, Tuesday, you will have watched the Lewis structure video. We'll talk about isoelectronic, and then we'll do examples of Lewis structure.